and differentiability, sheet 1. So the first problem of the sheet is about a function fx equal to x squared signum of box x plus fractional part of x, where x lies in the interval 0 to 2. For x greater than or equal to 2 but less than 4, it goes like sin x plus mod of x minus 3. We want to discuss this function for continuity and differentiability at points where there is change of behavior. All right. Now, fractional part of x essentially is x minus box x, isn't it? X minus box x. So fractional part of x changes behavior every time box x changes behavior, and box x changes behavior every time x is an integer. Yes or no? Right? So in the interval 0 to 2, fractional part of x, the point where fractional part of x would have to be investigated is x equal to 1 in the meat of this interval. 0 of course, but x equal to 1 is the point where fractional part of x will change behavior, right? Now box x will also change behavior at x equal to 1, right? So this interval then would have to be broken down into two intervals, 0 to 1 and then 1 to 2. That is how we will have to deal with it. So x greater than or equal to 0, less than 1. Let me not include 1 to begin with. Fractional part of x will be x. Fractional part of x will be x when x lies between 0 and 1. It itself is a fractional, and fractional part of x will be x. Yes or no? X. Box x would be 0. When x lies in this interval, box x would be 0, and signum 0 will be 0. 0 into x squared is 0. So that's simply 0, right? So this part becomes 0. Then for x greater than or equal to 1 but less than 2. So what I do is let me for the time being look at x equal to 1 separately, and let me see if I can merge. So just to give you a feel, let me look at x equal to 1 separately. What happens at x equal to 1? At x equal to 1, fractional part of x becomes 0. Box x is 1. Signum of box x would be plus 1, and this will be 1. So at x equal to 1, it assumes a value equal to 1. Yes or no? Right? Clear? For x greater than 1 but less than 2. X greater than 1 but less than 2. Fractional part of x will be what? X. See? Fractional part of x is given by x minus box x. That's fractional part of x. When x lies in the interval 1 to 2, what is box x? 1. So this will be x minus 1. This is going to be 1. Fractional part of x will become x minus 1. Yes or no? When x lies in the interval 1 to 2, fractional part of x will be x minus 1. Box x will be 1. Signum 1 would be 1, and this will be x squared. This will be x squared. Yes or no? Clear? So this interval broken down into sub-intervals and simpler functions, right? Now look at this. X greater than or equal to 2 but less than 4. Sin x doesn't change behavior anywhere, right? But mod x minus 3 changes behavior at x equal to 3. So x equal to 3 would be a node, so you would want to break this into 2 to 3 and then 3 to 4, right? So x greater than or equal to 2 but less than 3. Mod x minus 3 would be 3 minus x. Because x is less than 3, and sin x would be sin x itself. Yes or no? Right? And then from 3 to 4, x greater than or equal to 3 but less than 4. So if x is greater than or equal to 3 but less than 4, mod of x minus 3 would be x minus 3. And sin x would be sin x. Is it not? So this is the description of fx in various intervals, various logical intervals, simpler elementary formation of these lines of description. Now, to the left of 1, fx goes as x. At x equal to 1, it's 1. Now, one more thing. After you, see, once you grow up to all of this, you'll be able to, refine things. At x equal to 1, its value is 1. If you put x equal to 1 in this will also give me 1. So 1 could have been included in this interval. Yes or no? 1 could have been included in this interval. Then at x equal to 1, this will also give me 1. That means this line of description is redundant. 1 could have been included in this line of description. Yes or no? So x greater than or equal to 1, and I remove the redundancy from here. Clear? You realize whatever I've done here? Nahin? Right? So now, say x equal to 1. Let me examine fx at x equal to 1.
So that sin x is in degrees or radians?
Always in radians.
So but after pi the value will change.
So what?
So
There is no change of behavior. Sin x is still sin x. It is changing sign. Doesn't mean it will change behavior. See, if there is a line y equal to x, it is positive here and negative here, but both are y equal to x. Change of sign doesn't mean change of behavior. Change of sign doesn't mean change of behavior. If some other functional entity defines it in two intervals that across a point, that's when there is change of behavior. But there is no change of behavior because a function changes sign. No. Right? It's still described by sin x. And sin x is continuous for all x. Cos x is continuous for all x. There is no change, even not because it's polynomial. I mean, the tan inverse x also could be written in terms of polynomial, but there is discontinuity. So don't bother about that right now. The only thing that I want to tell you is that change of sign doesn't mean there is change of behavior. It's sin x to the left of 3 or sin x to the right of 3 will still be calculated by the same transcendental function sin x, right? Mod x minus 3 to the right of 3 goes as x minus 3, which is one kind of function, and to the left of 3 it goes as 3 minus x. That's change of behavior. So you must be very clear and transparent in your understanding of what it means by change of behavior, right? Now, at x equal to 1, to the left of 1 it goes as 1. So if I have to find limit fx, x tends to 1 from the less than 1 side. To the left of 1, the description of fx is x, right? So this is limit x tends to 1 from the less than 1 side, which is 1. So the left hand limit at 1 is 1, right? Limit fx, x tends to 1 from the greater than 1 side. When x is slightly greater than 1, hey, this is also greater than 1. This is also greater than 1. But we look at that interval which is just to the right of 1. Just to the right of 1 is this description, right? So to the right of 1, the description of fx is this quadratic, right? Is limit x squared plus x minus 1, x tends to 1 from the greater than 1 side, which is 1. So the left hand limit at 1 is 1, the right hand limit is 1, and the value of the function at x equal to 1 is what? 1. As you can see, the value at x equal to 1 is obtained by this line of description, which gives me 1. So limit fx, x tends to 1 from the left hand side is equal to limit fx, x tends to 1 from the greater than 1 side is equal to the value of the function at x equal to 1. This completes all the requirement towards meeting continuity at x equal to 1. So function is continuous at x equal to 1. Left hand limit at 1 is equal to right hand limit at 1 is equal to the value of the function at x equal to 1. The function therefore is rendered continuous at x equal to 1. Right? Now, If it is rendered continuous at x equal to 1, then derivability would have to be checked for. Did I tell you in my last class? Continuity will not guarantee derivability, but derivability will guarantee continuity. All right. Now, let me check on differentiability or derivability at x equal to 1. All right. Continuity is all right. It would be so much better if it was discontinuous at x equal to 1. Then that will reduce the burden of checking on differentiability. Right? So, but the point is, it is difficult to take that call whether to check differentiability first, or because if it turns out to be differentiable, then continuity may or may not happen. Continuity will happen, but if it is not differentiable at that point, then you will still have to check for continuity, right? So it's difficult to take a call if the complexity of the function is large, right? So then f dashed 1 minus 0, left hand derivative at x equal to 1 is like limit fx minus f1 by x minus 1 as x tends to 1 from the less than 1 side, right? But f1 is 1, as you could see, and fx when x is less than 1 is described by x. So this is like limit x minus 1 by x minus 1, x tends to 1 from the less than 1 side, and that's equal to 1. The left hand derivative at x equal to 1 is 1. The right hand derivative at x equal to 1 is limit fx minus f1 by x minus 1, x tends to 1 from the greater than 1 side. When x is slightly greater than 1, then this becomes the description. So fx becomes x squared plus x minus 1. f1 is 1, as you can see, minus 1 by x minus 1 as x tends to 1 from the greater than 1 side. Clear? Now this could be further written as limit x square plus x minus 2. This is x square plus x minus 2, which could be factorized as x minus 1 into x plus 2. Yes or no? X square plus x minus 2 could be factorized as x minus 1 into x plus 2 divided by x minus 1 as x tends to 1 from the greater than 1 side. And this becomes equal to 3. So the left hand derivative at 1 is 1, the right hand derivative at 1 is 3. The slope of the left hand tangent at 1 is 1, the slope of the right hand tangent at 1 is 3. Non-uniqueness of tangency at x equal to 1. Non-uniqueness of tangency at x equal to 1, therefore the function was not differentiable at x equal to 1. And therefore, if you had checked this, then you would still have to check continuity. Yes. So, got me right on this? So, function is not differentiable but continuous at x equal to 1. And let me also tell you, right now I want you to do this derivability test using first principles, but once you mature a little, then the left hand, once it's tested for continuity, it has passed the test of continuity, then differentiating to the left of 1 will give me 1, right? Then differentiate to the right of 1, immediate right of 1, it will give me 2x plus 1. At x equal to 1, it will become 3. That's directly differentiating, but I don't want you to directly differentiate now. I want you to do all of this from first principles, at least for some time, right? Huh? Right? So if you differentiate this 2x plus 1 at x equal to 1, it becomes 3. The right hand derivative at x equal to 1, right? So now the other point where you would have to check for continuity is 2, because to the left of 2 it goes like this, to the right of 2 it goes like this, right? Again we'll do using first principles only for some time. First let me check for continuity. Limit fx x tends to 2 from the less than 2 side is limit x squared plus x minus 1, x tends to 2 from the less than 2 side, right? So what will that be? 4 plus 2, 6 minus 1, 5. Yes or no? Left hand limit is, see, as x tends to 2 from the less than 2 is described by this, it will be 4 plus 2, 6 minus 1, 5, right? So the left hand limit at 2 is 5. Now the right hand limit at 2 obviously is not 5. Limit fx x tends to 2 from the greater than 2 side. Greater than 2 side is this, right? So this is going to be limit sine x plus 3 minus x as x tends to 2 from the greater than 2 side, which is like sine 2 plus 1. Sine 2 plus 1. Yes or no? So the left hand limit at 2 is not equal to the right hand limit at 2. Good riddance. We will not have to check for differentiability, right? Because it has not passed the test of continuity, right? So obviously the function is not differentiable. But now see, think of it, you know, at x equal to 2, the transformation that took place at x equal to 2 was because of this box function. You know, the box here changed behavior at x equal to 2. It caused loss of continuity at x equal to 2. The box will cause loss of continuity at x equal to 2, but mod x minus 3 didn't cause loss of continuity. So at x equal to 2, the box function was responsible for loss of continuity. The modulus did not play a part in loss of continuity. Modulus will not result in loss of continuity. Modulus will result, if at all, in loss of differentiability. But the box is largely responsible, mostly responsible for loss of continuity, right? Now, what's the other point that we want to check this function for? X equal to 3, because to the left of 3 it goes like this, to the right of 3 it goes like this. Now, I'm not expecting loss of continuity here, because at equal to 3 it was mod of x minus 3 that changed behavior and not sine x, right? So I'm not expecting loss of continuity, but at x equal to 3 mod of x minus 3 was not differentiable. See, at x equal to 3 mod of x minus 3 was not differentiable, because the graph of mod of x minus 3 is like this. Y equal to x minus 3 to the right of 3, y equal to 3 minus x to the left of 3. The right hand derivative would be the slope of this line, which is plus 1. The left hand derivative would be the slope of this line, which is minus 1. Therefore, this fellow caused loss of differentiability, would be entitled to cause differentiability at 3, but will not participate in loss of continuity at x equal to 3. So I'm expecting at x equal to 3 two things to happen. Number 1, continuity to prevail. Number 2, differentiability to be sacrificed at x equal to 3. This is my expectation at x equal to 3. Let's perform a reality check on this. Clear? Realize that at x equal to 3 mod of x minus 3 is not discontinuous, but it is not differentiable, right? So let's do a quick check on that. So continuity first, limit fx, x tends to 3 from the less than 3 side. When x is less than 3, this is the description. And as x tends to 3, this will tend to 0, this will tend to sine 3, right? So the left hand limit at 3 is sine 3, right? Then limit fx, x tends to 3 from the greater than 3 side. When x is greater than 3, this is the description. As x tends to 3 from the greater than 3 side, this tends to 0 and this tends to sine 3. So this will tend to sine 3. The value of the function at x equal to 3 can be obtained from this, which is sine 3. So f3 is also sine 3, which means the left hand limit at 3 is equal to the right hand limit at 3 is equal to the value of the function at x equal to 3. The function therefore, as expected, is continuous at x equal to 3, right? Now I am expecting the function to be not differentiable at x equal to 3, because mod of x minus 3 might have caused loss of differentiability at x equal to 3, but let's do a quick check on that. Okay, again from first principles. Without first principles, I can very easily see, if I differentiate this to the left, it will be cos x minus 1. So at x equal to 3, it will be cos 3 minus 3. To the right of 3, I have cos x plus 1. So cos 3 plus 3 would be the right hand derivative. So for sure, I am expecting, I am now convinced that it's not going to be differentiable at x equal to 3, but using first principles. Now let's go past it, right? So f dashed 3 minus 0 left hand derivative at x equal to 3. Left hand derivative at x equal to 3 is what? Is like limit fx minus f3 by x minus 3 as x tends to 3 from the less than 3 side. Now when x is slightly less than 3, this is the description of fx, right? So this is like limit sin x plus 3 minus x minus at x equal to 3, it's going to be sine 3. f3 is going to be sine 3. So minus sine 3 divided by x minus 3 as x tends to 3 from the less than 3 side. What do you say? So now I have like a sine c minus sine d. This by this will be minus 1. I club this to sine c minus sine d, right? So this would give me like limit 2 sine c minus d by 2, right? Cos c plus d by 2 divided by x minus 3. And this by this is going to be minus 1. So minus 1 as x tends to 3 from the less than 3 side. Clear? Now this 2 I can place here. As x tends to 3, x minus 3 by 2 tends to 0. As x tends to 3, x minus 3 by 2 tends to 0. So this is like sine theta by theta. As theta tends to 0, this is going to be 1. And as x tends to 3, this will tend to cos 3. This will become cos 3, yes or no? So this will then become cos 3 minus 1, which is the left hand derivative at x equal to 3, which is the left hand derivative at x equal to 3. Yes or no? Right? Let's obtain the right hand derivative at x equal to 3 in exactly the same way. Can I wipe this off? Can I wipe this off? F dashed 3 plus 0 is defined as hello fx minus f3 by x minus 3 as x tends to 3 from the greater than 3 side. When x is greater than 3, this is the description of fx, this is the description of fx, right? So this is like sin x plus x minus 3, and sin 3 is f3 is sin 3 like before, divided by x minus 3 as x tends to 3. Now exactly the same way, this by this will be 1, so plus 1, and then the x tends to 3, x tends to 3 from the greater than 3 side. So this will be sin x minus sin 3 by x minus 3 like before. Plus 1, and we've already dealt with this. This had turned out to be cos 3, right? This had turned out to be cos 3 using sin c minus sin d, so I'm not going to rewrite this. So this will be cos 3 plus 1, which is the right hand derivative at x equal to 3. Is the left hand derivative equal to the right hand derivative? No. The function therefore is not differentiable at x equal to 3. See, I will not talk of x equal to 0 because I do not know of what is happening to the left of 0. If the domain is not defined, no, in this case then I can extend it. X less than 0, I can still define this function, isn't it? Because for x slightly less than 0, we will not say anything. No, we will not comment on that. If I do not know what is happening to the function to the left of x equal to 0, then how will I comment? To the left of x equal to 0, it could have been sin x. So until and unless I know about what is to the left of x equal to 0, why would I unnecessarily comment on that, right? I would have to know about the function to comment about the function, right? Obviously, right? You will discuss a function only in regimes over which you have knowledge of the function, right? Right then, and let's look at the next one. Can I wipe this off? Are you all through with this? Right? Nothing difficult about it, isn't it? Fx is defined as fractional part of x plus 1/3 box of sine pi x, x greater than or equal to 0 less than 1, and is defined as box of 2x signum of x minus 4/3 for x greater than or equal to 1 but less than or equal to 2. We want to examine this function for continuity, differentiability, etc. Right? Okay, again, our task is to get rid of these fractional box, etc., and look at it as simpler looking functions. Break these intervals into subintervals over which the simplicity could be expressed. Same with the second line of description, right? Now, in the first line of description, 0 to 1, for example, this box of fx changes behavior for those values of x where fx is an integer. Yes or no? So in this case, in the interval 0 to 1 at x equal to half, this will become sine pi by 2 and this will become an integer. Yes or no? This will become sine pi by 2 and therefore an integer. Yes or no? At x equal to half, this will become sine pi by 2, which is 1, which is an integer. So x equal to half is a point in the meat of this interval where this changes behavior, right? Now, fractional part will change behavior every time the quantity inside becomes an integer. Now, in the interval 0 to 1, x equal to 2/3 is a point where this changes behavior, because at x equal to 2/3, this will become an integer. Yes or no? Right? So the two nodes in the meat of this interval 0 to 1 would be half and 2/3, half and 2/3. Yes or no? Right? So half and 2/3, half and 2/3. So we then want to break it up into 0 to half, half to 2/3, 2/3 to 1. Yes or no? Now, just to isolate 0 to begin with, I'll amalgamate the intervals subsequently, but just for the sake of analysis, at x equal to 0, which is a point, this will obviously become 0. Sine 0, it will become 0. fx is clearly 0 at x equal to 0. Right? Now, for x greater than 0 but less than half, this will be less than sine pi by 2. This will be less than 1. This quantity would be less than 1. Pi x will lie from 0 to pi by 2. So sine pi x will lie between 0 and 1, and box of sine pi x will be 0. Yes or no? Box of sine pi x will be 0. So in the interval 0 to half, it is 0. Now, which means I could have included 0 in this description. This then becomes redundant for me. Clear? Isn't it? Then, at x equal to half, this will become sine pi by 2. Box of 1, that makes it 1. And this will become, at x equal to half, 5 by 6. Fractional part of 5 by 6 would be 5 by 6 only. At x equal to half, this will become 5 by 6. And fractional part of 5 by 6 will be 5 by 6. So 1 into 5 by 6 at x equal to half. At x equal to half, the value of this function is 5 by 6. Now, then half to 2/3. Half to 2/3. Now, see, this will be greater than pi by 2 but less than 2 pi by 3. Yes or no? Pi x will be greater than pi by 2 but less than 2 pi by 3. Second quadrant. In the second quadrant, sine theta lies between 0 and 1. So box of sine theta will be 0. Box of sine theta will be 0. Then don't care about this. This anyways becomes 0 in this interval. Then at x equal to 2/3, zero, because this will become 0. And therefore, I could have included 2/3 in this description. Yes or no? Because 2/3 gives me 0. So might as well include this and prevent redundancy. At x equal to 2/3 at 0. Then 2/3 to 1. X greater than 2/3 but less than 1. What is it? When x is greater than 2/3 but less than 1, this will be greater than 2 pi by 3 but less than pi. So this will still be 0. This will still be 0, which means now I could have merged half to 1. I could have merged half to 1 because all along from half to 1, the value is 0. Yes or no? Are you confused? So I could have merged these intervals. So instead of 2 intervals, a neater expression would be x greater than half less than 1, because all the way from half to 1 it is 0. So what I do is I again economize this interval. Less than 1. Yes or no? It is 0. Clear? Is there any room for discontent? No? Okay. So this completely taken care of. This completely taken care of. Now let's handle this second interval. Let's handle this second interval. 1 to 2. 1 to 2. Now signum of something changes behavior when that something changes sign. This changes sign at x equal to 4 by 3. At x equal to 4 by 3. Now in the interval 1 to 2, this changes behavior every time 2x is an integer. 2x is an integer at 1, at 2, and at x equal to 1.5 also. At x equal to 1.5 also 2x is an integer, right? So then x equal to 1.5 means 3 by 2, there is change of behavior, right? At x equal to 4 by 3, this changes behavior. That means now I have my logical intervals available to me. 1 to 4/3, 4/3 to 3 by 2, and 3 by 2 to 2. Clear? Over which I will have to break this into simpler looking functions. Are you all there with me? Right? Now, see, at x equal to 1, for example, at x equal to 1, what does it turn out to be? This will box of 2, and this will be a negative number. So minus 2, yes or no? For x greater than 1, less than 4 by 3, 2x will be greater than 2 but less than 8 by 3. So box of 2x will still be 2, and x minus 4 by 3, signum of that will still be minus 1. So what I can do is x greater than or equal to 1 but less than 4 by 3. When x is less than 4 by 3, this is a negative number. Signum of this will be minus 1. And since x is greater than or equal to 1 but less than 4 by 3, 2x will be greater than or equal to 2 but less than 8 by 3, which is 2.67, right? So box of 2x will be 2. Box of 2x will be 2 in this interval. Yes or no? Right? So into 2. Then at x equal to 4 by 3, it will be 0. Because signum of 0 will be 0. Right? At x equal to 4 by 3, it's going to be 0. Right? Now, for x greater than 4 by 3 but less than 3 by 2. x greater than 4 by 3 means signum of a number which is positive, so this will be 1, and 2x will be less than 3 but will be greater than 2.67. Yes or no? So box of 2x will still be 2. Yes or no? Box of 2x will still be 2. Isn't it? When x is in this interval, 2x will be less than 3 but will be greater than 2.67. So box of 2x will be 2. Box of 2x will be 2 and this will be 1. So this will turn out to be 2 for x greater than 4 by 3 but less than 3 by 2. Then at x equal to 3 by 2, at x equal to 3 by 2, or for x greater than or equal to 3 by 2 but less than 2, this will still be 1. Signum will still be 1, and 2x will be greater than or equal to 3 but less than 4. So box of 2x will be 3. Box of 2x will be 3. Right? And then finally at x equal to 2, box of 4, 4 into 1, signum would be 1. So x equal to 2 isolated. So then, now we have the spectrum of intervals at our disposal, and now we can use these intervals to obtain continuity differentiability. What are the points that we want to examine? At x equal to half we want to examine, at x equal to 1, at x equal to 4 by 3, at x equal to 3 by 2. These are the points where we want to examine this function for continuity or differentiability. Is the idea clear? So I'm not doing that continuity test for you on this. Now the description is available. You are adequately equipped to carry out the test on continuity and differentiability as per the norms. Clear? Let's move to the next problem. Three, fx is given to be cos of sin x minus cos x by x squared when x is not equal to 0 and is a when x is equal to 0. Right? We want to find the value of a for which fx is rendered continuous at x equal to 0. Now for continuity at x equal to 0, what is required? For continuity at x equal to 0, we must have limit fx x tends to 0 equal to f0. This is the requirement. X tends to 0 is f0. This will guarantee continuity at x equal to 0, isn't it? Limit fx x tends to 0 must be f0. That must guarantee continuity at x equal to 0. That means limit fx x tends to 0, which is f0. f0 is given to be a. So a must be limit fx x tends to 0. Right? So all that you need to do is, and as x tends to 0, it's not about what is happening at x equal to 0. It's about what is happening in the neighborhood of x equal to 0. In the neighborhood of x equal to 0, this is what is happening. Right? So when I find this limit, I will use this as the description because this describes the neighborhood of x equal to 0. X is not 0 means neighborhood of x equal to 0. So then limit fx x tends to 0 is like limit cos of sin x minus cos of x divided by x squared as x tends to 0. Right? I have to then evaluate this limit. I'm not allowing L'Hopital's rule. I'm not allowing series expansion. Right? I would then take recourse to first principles, cos c minus cos d. 2 sine d minus c by 2 sine c plus d by 2. That's what I'm going to do. Right? 2 sine d minus c by 2 into sine c plus d by 2 by x squared as x tends to 0. Is it or is it not? Right? This I could further write as twice limit sine x minus sine x by 2 divided by x minus sine x by 2. I'll tell you why I did this. Into sine x plus sine x by 2. And I reinforce in the denominator from an alien entity x plus sine x by 2, and then I reinforce it with x squared minus sine squared x by 4, and then there is an x square already sitting in there. You realize why I did this? Because as x tends to 0, x minus sine x by 2 also tends to 0, sine theta by theta. So I had to bring it of the form to the form sine theta by theta is theta tends to 0. Same with this, sine theta by theta is, and then I balance these two terms, x square minus sine squared x by 4 I balanced, and x squared I allowed it to sit there neatly. Yes or no? Now very simple. This will be 1, this will be 1, and x square minus sine squared x by 4, realize, could be written as, of course, that 4 sitting there, x squared by x squared minus sine squared x by x squared. This tends to 1, this tends to 1, so this tends to 0. So this limit will be 0, because this is 1, 1, 2 by 4 into 0, 1 minus 0, 1 minus 1, that makes it 0. So this limit is 0. So f0 must be a, which must be 0. This is f0, this is f0, and this must be equal to a for continuity at x0. Yes or no? Right? Your attention, please. Fx is mod of x plus half into box x for x lying in the interval minus 2 to 2. For x lying in the interval minus 2 to 2. I want to examine this function for continuity differentiability wherever applicable, wherever applicable. Clear? Now again, this is mod x, so in the interval minus 2 to 2, box x will change behavior at minus 1, 0, plus 1, right? For box x, the nodes produced in this interval are minus 1, 0, and plus 1 are the nodes that this will produce in the interval minus 2 to 2. Minus 1, 0, plus 1. These are the nodes produced, right? Now, this will produce a node at minus half. Mod x plus half will produce a node at minus half, right? Yes or no? Mod x minus a will produce a node at x equal to a, right? So x equal to minus half is the point where this produces a node, and minus half is somewhere here, right? So my relevant intervals of description would be 1, 2, 3, 4, 5. These would be my relevant intervals of description of this function, right? Now, for x greater than or equal to minus 2, but less than minus 1, mod x plus half. So this is, so what? This could, mod of the product is product of the moduli, isn't it? Huh? Isn't it? Why afterwards? You could apply earlier also. Will it change anything? Mod AB is mod A into mod B, isn't it? So it's going to give me the same thing. Yes or no? Right now? So minus 2 to minus 1. What is box x? Minus 2. What is mod of box x? 2. And since x is in this interval, x is less than minus half, so mod of x plus half would be minus of x plus half, because x plus half will be negative. When x lies in this interval, that means x is less than minus half as well. That means x less than minus half means x plus half will be negative, and mod of x plus half would be minus of x plus half. Yes or no? Right? Do you all understand this? Clear, no? Now, minus 1 to minus half. Less than minus half, for example. Now, when x is less than minus half, x plus half is negative, and like before, mod x plus half would be minus of x plus half. And x in this interval means box x will be minus 1 and mod of box x will be plus 1. Yes or no? Then x greater than or equal to minus half but less than 0. In this interval, box x will still be minus 1, box x will still be minus 1, mod of box x will be plus 1. And since x is greater than or equal to minus x plus half is greater than or equal to 0, so mod of x plus half will be x plus half, x plus half. Right? And then x greater than or equal to 0 but less than 1, box x will anyways be 0. So this will turn out to be 0. For x greater than or equal to 1 but less than 2, box x will be 1 and mod of x plus half will be x plus half because x plus half is positive. This is fx in various intervals. Yes or no? So what are the points where you would examine this function? Minus 1, minus half, 0, 1. Do I need to do it for you, or you will be able to manage both continuity and differentiability of this function at these points where there is a definite change of behavior, right? Proceed? Shall I proceed then? Fx is 2 tan x plus 5x minus 2. I want to see if this has a root in the interval 0 to pi by 4. I want to see if in this interval this has a root. Now, tan x is continuous everywhere from 0 to pi by 4. 5x minus 2 is a polynomial continuous everywhere. That means in the interval 0 to pi by 4, fx is continuous. Fx is continuous in the interval 0 to pi by 4. Now, if it happens that f0 and f pi by 4 are of opposite signs, that means if a continuous function changes sign in an interval, it must have a root in that interval, yes or no? So let me quickly perform that check, right? See, if it didn't change sign, doesn't mean it will not have a root, but if it changes sign, it will certainly have a root, right? So f0, the problem would arise if it didn't change sign, then I would have to deal with further investigation. But if it does change sign and it is found to be continuous, then my problem becomes simpler to handle. So f0 is minus 2, yes or no? Right? F pi by 4 is 2 plus 5 pi by 4 minus 2, which is positive, yes or no? This is negative. So fx changes sign in the interval 0 to pi by 4. f0 into f pi by 4 is negative. Therefore, if fx is continuous, then it must have a root in the interval 0 to pi by 4. Fx is indeed continuous in the interval 0 to pi by 4. So it does have a root in that interval, right? It's given that fx is x plus fractional part of x plus x sine fractional part of x when x is not 0 and is 0 when x is 0. We need to then examine this function for continuity at x equal to 0. Clear? The value of the function at x equal to 0 is 0. I want to check for continuity at x equal to 0. Right? Now, limit fx x tends to 0 from the greater than 0 side. See, fractional part of x, your attention please, has a graph like this. At x equal to 0, it's 0. This is the graph of fractional part of x. Yes or no? Around x equal to 0, this is what you would witness, right? Now, as x tends to 0 from the greater than 0 side, this tends to 0 anyways. Now, as x tends to 0 from the greater than 0 side, realize this is fractional part of x at any given x. This is fractional part of x. This comes closer and closer and closer to 0, right? So this tends to 0. This anyways tends to 0. So the right hand limit at x equal to 0 is 0, right? Limit fx, x tends to 0 from the less than 0 side. This will be 0. Now, as x tends to 0 from the less than 0 side, this is fractional part. It comes closer. It never becomes equal to 1, but could be brought as close to 1 as you like. Yes or no? So the left hand limit at x equal to 0, fractional part of x comes closer and closer and closer and closer to 1. So the left hand limit is 1. So this will become 1 plus. This anyways tends to 0. This anyways tends to 0. So this becomes 1. So the left hand limit is not equal to the right hand limit at x equal to 0. Is it discontinuous? Yes. What's the nature of discontinuity? Non-removable discontinuity. Non-removable discontinuity because the left hand limit is not equal to the right hand limit. It possesses non-removable discontinuity at x equal to 0. Non-removable discontinuity at x equal to 0 is what it presents. Clear? Number 7. Fx is defined as maximum of root 4 minus x squared comma root 1 plus x squared for x lying in the interval minus 2 to 0 for x greater than 0 less than or equal to 2. It's defined as minimum of root 4 minus x squared we want to examine this function for continuity differentiability in this interval. Clear? See, these problems are solved graphically. There are two functions essentially involved here. One is root 4 minus x squared, is 1 plus x squared, right? Now, and in the interval minus 2 to 2. Now, y equal to root 4 minus x squared is really is a semicircle because upper half, y is only positive. Root 4 minus x square can never be negative. So it's half of a circle centered at 0, 0 and radius 2. See, because this can be written as x square plus y squared equal to 4. Where y cannot be negative. Yes or no? If you square this, x square plus y. So this is part of a circle. This circle center 0, 0 and radius 2. But which part of the circle? Part of the circle in which y is greater than or equal to 0. Yes or no? So this essentially represents y equal to root 4 minus x squared doesn't represent the full circle, doesn't represent this dotted line, but it represents only the solid line, minus 2 to 0. This is the graph of y equal to root 4 minus x squared. Yes or no? Now, 2. Now, root 1 plus x squared. Y equal to root 1 plus x squared, you know one thing for sure. Y is never negative. And if x comma y satisfies this, then minus x comma y will also satisfy this, isn't it? If x comma y, p x comma y lies on the graph of the function, then minus x comma y will also lie on the graph of the function. Yes or no? That means, and p prime will be mirror images of each other about the y-axis. That means the graph of y equal to root 1 plus x squared must be symmetric about the y-axis. Yes or no? Must be symmetric about the y-axis. And in the first quadrant, as x increases, y increases. You can see that as x is increasing, y is increasing. Yes or no? Which means, if I have to draw the graph, let's say in the first quadrant of y equal to root 1 plus x squared, at x equal to 0, it's 1, and then it increases like this. Not a parabolic increase, but just an increase. Right? Y equal to root y, as x tends to infinity, y will tend to infinity. And since it's symmetric about the y-axis, the same plot will exist to the left of the y-axis. This then turns out to be our graph of y equal to root 1 plus x squared. Is that all right with everyone or not all right? No? Clear? Now what I do is, this is a circle and this is y equal to root 1 plus x squared. Let me plot them in the same xy plane. Let me plot both these curves in the same xy plane. Let me plot them together. Clear? If you allow me to remove the clutter from here. Have you all registered whatever I have communicated in this? Wipe this off. In the same xy plane, let me plot both of them. Right? This is y equal to root 1 plus x squared. And this is y equal to this semicircle 4 minus x squared. Yes or no? Now the point where they intersect would be the point where 4 minus x squared becomes equal to 1 plus x squared. They have the same y for these values of x. Yes or no? These two graphs y equal to root 1 plus x squared would intersect with this. When for the same x they have the same y, that means when this equal to this, when the y for this for a given x is the y for this for the same x, that means when this happens, that means when 2x squared becomes equal to 3, or when x equals plus minus root 3 by 2, that's when they intersect. These are the intersection points. X equal to plus minus root 3 by 2, minus root 3 by 2, plus root 3 by 2. These are the points where they intersect. Clear? Yes or no? At x equal to plus minus square root of 3 by 2, their y's will become the same. So these would be common points on the graph of the two functions. Clear? Now, let's start by performing the bit on this description. Okay? Can I remove this portion? Just create some room. Now, from minus 2 to 0. Minus 2 to 0, which includes both minus 2 and 0, which includes both minus 2 and 0. What prevails is the larger of these two. Between minus 2 and 0, inclusive of the endpoints, what prevails is whichever is larger. That means whichever graph is higher. will prevail. Yes or no? Larger means it's going to have a greater y, means it will be higher than the other graph. So then, between minus 2 to minus 3 by 2, minus root 3 by 2, this is larger. This is larger, yes or no? If this is larger, that means this goes away. Yes or no? Then from minus root 3 by 2 to 0, which is larger? The semicircle is larger, right? So this will go away. Yes or no? This is a point on the graph. This is a point on the graph. So far so good? Clear? Then between 0 to 2 by 2, excluding 0. Because at 0, this is a point on the graph. But at x greater than 0, less than or equal to 2, the smaller of these two will prevail. That means the graph which is lower will prevail. The one that has a smaller y will prevail. Now, between 0 to this point, which is smaller, y equal to root. So this will pass away. And this will be a kink, because at x equal to 0, this is a point on the graph of the function. This is a kink from 0 to root 3 by 2. Then from root 3 by 2 to 2, this will prevail, or the semicircle? Semicircle will prevail. That means this will go away. Smaller is this. And this is indeed a point on the graph. This is a kink. This is the graph of y equal to, this is the graph of y equal to fx. This is the graph of y equal to fx. Yes or no? Do you all register this? Do you all register this? Yes or no? Right? Now, don't do any hanky-panky. Just by the graph. At this point, it is continuous very clearly, but not differentiable, because again, just this will be my left hand tangent, this will be my right hand tangent, as you can see. Visual inspection. Therefore, it is not, it is continuous at that point, but not differentiable, right? Now, come to 0. The left hand limit is this, the right hand limit is this. Not continuous, so no question of differentiability. Then at this point, continuous, but again not differentiable. This is my left hand tangent, this is my right hand tangent. Visual inspection. So continuous at this point, but not differentiable. We've graphically analyzed the whole thing without taking recourse to any messy algebra. Clear? There is, again, like we saw in 7, you know, this is also part of our learning of terminology associated, jargon associated. Same with problem 8. You know, we will learn a new jargon by means of 8, a new expression by means of 8. So let me get you past, and this is like a very favorite for examiners. They like to set a lot of things in and around this description. The description, as is suggested in problem 8, fx is given to be x minus x squared and gx is given to be maximum of ft t lying between 0 and x and x lying between 0 and 1. T lying between 0 and x, whereas x lies between 0 and 1. Please understand this, and I will explain although. Gx is given by maximum ft and is sine pi x for x greater than 0. It must be greater than 1. I don't think it makes sense greater than 0. It must be x greater than 1, because between 0 and 1, this is the description, so this must be x greater than 1. All right. Let us, hello, yeah. Let us now try and draw the graph of gx. from fx. Gx bears inheritance from fx, and that inheritance, the genetic constitution of that inheritance is given by this line of description. How do I obtain gx from fx? That's a question, right? So the first thing, the mother function is fx, from which gx would have to be obtained. Y equal to x minus x squared is what? A downward opening parabola with roots 0 and 1, isn't it? Y equal to x minus x squared is a downward opening parabola. Coefficient of x square is negative. Downward opening parabola with roots 0 and 1, right? This is the graph of y equal to fx. Zero to 1. At x equal to half, it becomes maximum and is equal to 1/4. Half minus 1 by 4, which is 1/4. Right? This is the graph of fx. Now, let us see what this means. In the interval 0 to 1, fx is described like this, and in the interval 0 to 1, gx is described like this. Please understand this notation right now, right here. Books will give you a very shoddy feel for the whole thing, but it's such a simple thing. Make sure you understand this when I am communicating. It's very simple. For any given x, fx is known. For any given x, for a given x, fx is known, right? Fx is this. Fx is x minus x squared. For any given x, the value of fx will be this ordinate. Yes or no? Which would be x minus x squared. But I want to find, for a given x, the value of gx. Now, what does this say really? What does this really say? Just to create some more space. For a given x, this is my fx. What does it really say? It says, in order to find gx at a given x, which lies in the interval 0 to 1, for a given x that lies in the interval 0 to 1, it says, pick on a running variable t. For a given x, I want to find gx. Given the knowledge of fx, pick on a running variable t. Pick on a running variable t. Now that t will run from 0 to x. That t will run from 0 to x. Now there is a t which I pick on, and that t runs from 0 to x. That t runs from 0 to x. Now while that t runs from 0 to x, it generates a lot of ordinates called ft's. For every t, there is going to be an ft, which is this, isn't it? This will be my ft, isn't it? For a given t, this is my ft, right? While this t, so objective, given x, this is the value of fx, but I want to find the value of gx. What's the rule for finding gx? The rule for finding gx is, for a given x, if this is fx, it says, take a running variable t and allow that running variable to run from 0 to x. Allow that running variable to run from 0 to x. While this runs from 0 to x, a large number of ft's would be t. For any given t in the interval 0 to x, these ft's will be produced, right? When t runs from 0 to x, there is f0, etc., ft's are produced, right? Of all the ft's that are produced while t runs from 0 to x, select the greatest ft. Select the greatest ft, and that will be gx. Select the greatest ft, and that will be gx. Yes or no? Which means, if there is an x that is less than or equal to half, but greater than or equal to 0. If there is an x that lies in this interval, 0 to half, then do you realize that while t runs from 0 to x, the greatest ft will be fx. The greatest ft will be fx, yes or no? If there is an x that lies in the interval 0 to half, if there is an x that lies in the interval 0 to half, then of all the ft's generated, the greatest ft will be fx itself. If there is an x here, of all the ft's produced, the greatest ft will be fx, yes or no? Which means in the and that ft, the greatest ft will also be gx, right? So for this interval, gx, which is maximum ft, will be fx itself, yes or no? Now, however, so far so good. Now I change the interval. Have you all assimilated this idea? No confusion. Now, what I do is, you can draw a new view. If there is an x greater than half but less than 1, if there is an x greater than half but less than or equal to 1, this x, that means for x greater than half, say less than or equal to 1, for x floating in this interval, this is my fx, yes or no? Now I know fx, but I need to find gx. To find gx, what am I going to do? I'm going to select a running variable t. This is my running variable t chosen, and this running variable t is guided to run between 0 and x. This t will run between this 0 and this x, for which I want to find gx. While it does so, it proposes these ft's. All these ft's are produced, right? While t runs from 0 to x, a large number of these ordinates are produced. This guy says that of all the ft's that are produced, select the greatest ft. So if x lies here, then what's the greatest ft produced? 1/4. 1/4 is produced at half but is equal to 1/4. This length is 1/4. Yes or no? So if x is greater than half, less than or equal to 1, then a t running from 0 to x, generating these ft's, the greatest ft produced would be ft equal to 1/4. Yes or no? So then, for x lying from half to 1, the greatest ft would be 1/4. Does it make sense to you or not? And then, of course, for x greater than 1, it is sine pi x. Which means, now let me draw the graph of gx. So I have an algebraic description of gx. Let me draw the graph of gx then. Clear? Can I wipe this off? See, if it was not max and it was min, then you select the smallest ft of all the ft's generated. Sometimes it will be max, sometimes it will be min, right? But the idea is the same. So the intervals are 0 to half, gx and fx are the same. The graph of fx was a parabola. X equal to 0 to half. The graph of gx and fx will be the same and will be equal to this parabola, part of the parabola. Right? Then, from half to 1, gx will be a constant equal to 1/4. And then for x greater than 1, so at x equal to 1, it's 1/4. This is a point on the graph of the function, 1/4. And then for x greater than 1, it will go like a sine pi x. So then the right hand limit sine pi, which is 0, which will not be a point on the graph of the function, but for x greater than up to a certain point, this will lie in the third, fourth quadrant, etc. It will be negative, sine graph negative, then it will go like this, etc. This is x equal to 1. At x equal to 3 by 2, it will be sine 3 pi by 2, so will be minus 1, which will be minus 1, and so on and so forth. After that, of course, there is no issue. This is the graph. So for sure, at x equal to 1, there is discontinuity and therefore loss of differentiability. For x greater than 1, no loss of discontinuity, no loss of continuity, no loss of differentiability. But at x equal to 1, it's not continuous and therefore not differentiable. The other point that you would have to examine is x equal to half. It is continuous, as you can see. No, but let me see, maybe not. Maybe it is differentiable because, see, this is part of the, this is the right hand tangent, as you can see, right? In a parabola, look at the left hand tangent at half. In a parabola, if you draw a tangent at this, left hand tangent will be this. And the right hand tangent anyways is an extension of this. Therefore, at x equal to half, it is differentiable also, because we can quickly check what's the big deal about it. But I can say, guarantee you, it will be differentiable because at x equal to half, the left hand tangent is this, the right hand tangent is this. In this, the right hand tangent is this and the left hand tangent will be simply this. So the left hand and the right hand tangents will match with each other. It will be differentiable, but let's quickly check. Right? But do you understand the looks of gx? Right? Now, let me check at x equal to half. Continuous for sure. At x equal to half, continuous for sure. Fx is x minus x squared. X minus x squared. At x equal to half, this will become 1 by 4. Right, left hand limit is 1 by 4, right hand limit is 1 by 4, which we could see from the graph as well. So continuity is not a issue. Let me check for differentiability at x equal to half. The right hand derivative is very simply 0, as you can see, because it's a constant function. The slope of this tangent is 0. Let me just find the left hand tangent at slope of the left hand tangent at half. So f dashed half minus 0 is limit fx minus f half by x minus half as x tends to half from the less than half side. When x is less than half, then fx is described as x minus x squared, right? Minus 1 by 4. Yes or no? What will this be? See, to the left of half, it is x minus x squared. Value at x equal to half is half minus 1/4, which is 1/4, divided by x minus half. What is this? Huh? What will this be? Yes, absolutely. You can see this is a perfect square. Limit x minus of x minus half whole squared divided by x minus half. Do you see that? As x tends to half, very clearly this is 0. So the left hand tangent has 0 slope. The right hand tangent visual inspection suggests that it has 0 slope. The function therefore is differentiable at x equal to half, and of course continuous for sure. Clear?